So here's the example that I've mentioned already in the past. So if the relation is a relation between students, and the relation is if you have the same letter, if your name starts with the same letter as someone else, you are related, right? In this case, then we would have a bunch of people here, right? So maybe Alice is here. Alice, well, I mean Alex, I guess. Alex, Alice, and so on. All these people are related. So if they are related, they are put into the same class. Then there's another class of a person named Ben, Bruno, and so on. There's a person for C and so on. So what I'm actually doing is, instead of addressing you as individuals, I am addressing you as groups. So there's an equivalence class for the letter A, there's an equivalence class for the letter B, and right, D and so on, right? So this is, in a way, how I'm partitioning the group. Now, why is it important that this is an equivalence relation? Because if this isn't an equivalence relation, I don't get a proper partition. For example, I don't want these groups to overlap, right? I don't want anyone to be in two groups at the same time. That will cause confusion, and then I won't be able to address you as A if this is ambiguous, right? In the case of functions, if I take a function instead of an equivalence relation, this could happen, right? These groups could overlap. I could have a bunch of elements being sent to the same element in case I have like non-injective function or something. So this is the main idea, and we will look at very specific examples of equivalence relations. I think I'm not going to give an example right now. You already have all the context you need to solve the exercises so far that I've given you so far, and I will give you more examples than you want. Like you will be sick of the examples of equivalence classes that we will cover. Okay, here's a question. Would the equivalence class always create a complete connected component, but relation may not? Okay, that's an interesting question. So in a way, the reason why we want an equivalence class, there's just two reasons I want an equivalence class. First, I want an equivalence relation. There's only two reasons why I need an equivalence relation. First, I need reflexivity so that every person is covered, right? Reflexivity means every person is related to itself, to themselves. So every person is at the very least inside the class represented by themselves, right? So I want to cover the entire class. Maybe there's some weird relation in which some people are not related to anything, then those would be left out. They will not be inside some class. I don't want that, and that's why I need reflexivity, right? The reason I need transitivity is so that these classes don't overlap. That is the second thing I want. These need not be necessarily connected or complete connected in the sense that you might be thinking. There are some more abstract ways you can think about this. For example, so one example that we will cover in probably in 2 weeks is that once we have constructed the integers, there will be a way for me to define an equivalence relation on the integers that will group everything, for example, all the even numbers together, right? So I will group the 0, I will group 2, I will group 4, and so on. So this class is definitely not connected, right? It is being separated by the other class. They still satisfy everything I want. They are disjoint, they contain, every number is contained in one of these classes, and so on. But this class is disconnected, right? In that sense. What other property do I want? Oh yeah, and the symmetry is just so that the order doesn't matter. Yes, you're welcome. Okay, let me erase this example since we haven't mentioned the integers, and we will do this in more detail. Okay, now any questions on what I've done so far? Any questions on equivalence relations? I know I haven't given many examples of this, given you some. We will cover so many examples of equivalence relations in the future. And okay, there's one more thing I should probably mention. So the quotient, let be an equivalence relation on X. The quotient, again, the quotient. So you already know how to multiply sets, and now I'm teaching you how to divide them in a way. An equivalence is just, sorry, a relation is just a set, right? So the quotient is defined as x divided by this, and this is defined as the set of all classes. Why don't I just take it like this? Right? So in our example, in our very abstract example, what would be the thing that I try to explain? So maybe let me write this in more detail. So let's say that X is the class of Mat 246, and the relation is two students are related if they start students if they start with the same letter. So maybe I should say names of students. So this isn't that weird. Names of students, they're related, they start with the same letter. This is an equivalence relation, of course. And then what would be the quotient? Well, the quotient would be, there's a class that contains Alice, which happens to be the same class as the one that contains Alex, because those two are related, right? So that's actually just the same class. I don't have to list it twice. There's a class for Bob, which is the same as everyone who starts with B. There's a class for Charlie, I don't know, and so on, right? In other words, I've reduced the set of students or names of students to just letters A, B, C, and so on, right? I've compactified you in a way so that I can address you more easily, more comfortably, or for reasons that will be made clear next week. Next week, I will give you the first concrete example with proofs of a quotient. And here's the thing that blew my mind the first time I saw it. The integers are a quotient. The rational numbers are a quotient. If I may add some more details, the integers are a quotient over the natural numbers. The rational numbers are a quotient over the integers, and the real numbers are a quotient on something kind of weird. But we will look at that in more detail. And when we construct how do you call this? Modular arithmetic, modular classes, those will also be quotients on the integers, but different quotients. We will get a different quotient every time, right? So there's a lot of examples coming. So if you find this definition a bit abstract, then don't worry. There will be plenty of examples, but keep in mind that this is an idea that shows up all the time. Someone, Yang, I think, mentioned in the chat something about connected. The word connected is related to topology, and there is a chapter in this course about topology. So if you think about this in a topological sense, if you want to think about shapes and geometry and deformations and stuff, the quotient is like gluing things together, right? I'm gluing all the students whose names start with the letter A into one bit and the letter B and so on. But I can do this in an abstract space, right? So for example, I could glue what would make sense in this scenario. If I won't draw this because it won't make sense right now, but if I have a square, like a sheet of paper, like a square sheet of paper, I could glue the edges together in such a way that what I get is like a donut, like a torus, right? This might be a little hard to visualize, and maybe I should have brought like a drawing. I could do that for the topology chapter. But quotients are like gluing things together, right? And the equivalence relation is basically telling you what things are you identifying? What points are you going to assume that they are pretty much the same? The same way that here, for me, for this example, Alex and Alice are like the same, not the same person, but the same object, because I only want to address you as groups of letters, for example. So the most important thing about these quotients is that quotients are partitions. A quotient is just a partition on a set. And I won't define partition to you because I think I've defined plenty of things in this class already, and we won't really deal with abstract partitions at any point. And there is an exercise in the first problem set that tells you that if you have a function that is, I believe, surjective, then the fibers or the inverse images of that function forms a partition or forms an equivalence relation. In our example, this function could be for every student, the function takes the student as input and outputs the first letter of the name, right? That would be the example in this case. Something that is in the additional problems that you can take a look at is that all of these arrows are reversible, right? Partitions, quotients, and functions are, in a very abstract sense, surjective functions, I should say, are all the same things, all the same thing. All of these things are the same abstract concept, right? And this is why, like I said in the past, this is an invitation to think about these abstract things. Okay, I will pause recording